So in this video we're going to establish the inverse of the tangent function, or the arctangent. And the process that we're going to walk through is going to be similar to the one that we did for both the sine and the cosine function at this point. So the first thing that we want to identify is that the tangent function is not one-to-one. And one way that we can verify that it's not one-to-one is to apply the horizontal line test, which we fail because the horizontal line intersects the tangent in more than one place. And because it fails the horizontal line test, it is a function that is not one-to-one and therefore is not invertible. It does not have an inverse. And because it doesn't pass the horizontal line test, what would happen if we tried to reflect it in the line y equal x? So remember, to find the image of an inverse function, we graph the function, we reflect the graph of the function in the line y equal x, and the reflection in the line y equal x is the inverse graph. And so the issue is, in this case, that if we reflect the tangent line in the line y equal x, because it didn't pass the horizontal line test, it fails to pass, the reflection fails to pass the vertical line test and isn't a function. So what we need to do is the same thing that we did with sine and cosine. We need to restrict the domain of the tangent function so that it is a one-to-one function. So what we want to notice is that if we go to the tangent function's vertical asymptotes that are located at negative pi over 2 and pi over 2, and we restrict the domain to run between those two vertical asymptotes, then we will get an image that passes the horizontal line test. So if I graph just the part of the tangent function between negative pi over 2 and pi over 2, I now pass the horizontal line test, so I have a function that is invertible. I can reflect it in the line y equal x. Before we go any further, though, let's just quickly establish what we already know about the tangent function. So some things that we know. We know that the tangent function, from a unit circle perspective, is just the ratio of the y coordinate to the x coordinate on the unit circle. In other words, the tangent outputs are found by doing y divided by x. And the input to the tangent function is the angle theta that we sweep through in standard form to get to the terminal side established by the xy coordinate. So our outputs are ratios y over x. If we give it a function name or put it in these outputs in function notation, it's a function of theta. You input angles. The name we give the tangent function is tangent, or tan of theta in function notation. Our goal is to get a function that is invertible, so we're going to restrict the domain to get a one-to-one graph. So we're going to restrict the domain to the open interval from negative pi over 2 to pi over 2. So between the two vertical asymptotes, we can't do a closed interval because we can't plug negative pi over 2 or pi over 2 into the tangent function. It's undefined at those values. So we restrict the domain. We want to identify the range associated with that restricted domain. And what we see is that the tangent function goes to negative infinity and goes to positive infinity. It's a continuous graph, so there's no breaks in it. So the range is negative infinity to positive infinity. And if I were being more careful, which I want to be, I would say that the domain, let's be a little bit more specific, the domain is going to be any angle on the restricted domain from negative pi over 2 to pi over 2. So in terms of the unit circle, we're going to be restricting our conversation to run from negative pi over 2 to pi over 2. So we're going to be talking about side ratios in quadrants 1 and 4 only. And the y coordinates are coming from quadrants 1 and 4. And the range which is the output, that's the y divided by x, the range, are going to be side ratios y divided by x on the interval from -1 to infinity. And then we want to notice that the tangent function, when we first established it, we had found some key points on it that we used to help us with graphing. So let's keep track of those key things. We have vertical asymptotes. This one's at x equals pi over 2. This one's at x equals negative pi over 2. The origin was a key point that we established. It has 0, 0. And then we said halfway between 0 and pi over 2, or halfway between 0 and 90 degrees, we have that 45-degree angle, or pi over 4 radians, associated with an output of 1. This was a special point. So this was the point input pi over 4 radians, output 1. And halfway between 0 and negative 90 degrees, or negative pi over 2, we had negative 45 degrees, or negative pi over 4, being associated with an output of negative 1 on the function. So we input negative pi over 4. The output ratio is negative 1. And those are kind of the key things that we kept track of when we were graphing the one period of the tangent function. So the key is, to get the inverse function, we're going to reflect the tangent function over its restricted domain in the line y equals x. And when we reflect it in the line y equal x, all of these key points get reflected over the line y equal x as well, and the asymptotes get reflected over the line y equal x as well. So I'm going to start by reflecting the tangent function. So there's the reflection of the tangent function right there. That is the inverse tangent function. Notice that these points all get reflected. The origin stays put, but this point reflects across to here, and we wind up at this point getting input 1, output the angle pi over 4. We reflect this point across to here. We get input negative 1, output the angle negative pi over 4. So we're switching the inputs and outputs. But the vertical asymptotes also get reflected as well. So we wind up reflecting those vertical asymptotes. So x equals pi over 2 gets reflected and becomes y equals pi over 2, and x equals negative pi over 2 gets reflected and becomes y equals negative pi over 2. So the vertical asymptotes for the tangent function get reflected and become horizontal asymptotes for the inverse tangent function. So let me grab my eraser and clean this mess up just so we can see the inverse tangent function a little bit more clearly. So here's the inverse tangent function. It has horizontal asymptotes at y equals pi over 2 because the tangent had a vertical asymptote at x equals pi over 2, and we have a horizontal asymptote at y equals negative pi over 2 radians coming from the reflected asymptote x equals negative pi over 2. So the tangent function, when we go to establish it, what we want to recognize is the outputs are, so this is the inverse. I hate how I have to go up here to grab the eraser. I'm used to working in PowerPoint and the eraser is easier to grab. So the inverse function, here's what we know about it. We know that the outputs are going to be the inputs of the tangent function. So the inverse function, the outputs will be angles. So if I'm going to use inverse function notation, it's going to be f inverse of, what do we input into the inverse function? We put the side ratios y divided by x into it. The inputs are y over x's. The tangent function can be given the inverse notation. So tangent inverse of, what do we put in? We put y over x into the inverse tangent. We don't put angles into it. We put y over x. Or the other name that we use is arctan of, and what goes in? Y over x goes in. And we output the angle between negative pi over 2 and pi over 2. So the domain of the inverse tangent function has to be the range of the tangent function, because the domain becomes the range and the range becomes the domain. So we see we can put in anything from negative infinity to infinity. You get to put in anything that you wish for a side ratio. The domain is going to be side ratios y over x running from negative infinity to infinity, and the range, the outputs, are going to be angles, but the angle outputs are restricted to the open interval from negative pi over 2 to pi over 2.